In this tutorial, we are going to talk about the Laplace transforms of hyperbolic functions, the sine hyperbolic function of at and the cosine hyperbolic function of at. So in my previous video, we talked about the hyperbolic functions of the trig function, which is the sine of at and the cosine of at. So in this video, we are going to talk about the Laplace transforms of these hyperbolic functions. So let's start with the definition of the Laplace transform of a function f of t. So this is equals to the integral from 0 to infinity of e raised to the power negative st. This is multiplied by the function f of t dt. So this is the function that we are seeking to transform into the s domain, which is the capital F of s. Alright, cool. So let's start with the sine hyperbolic function of at. So we are going to find the Laplace transform of the sine hyperbolic of at. Alright, so this is equal to the integral from 0 to infinity e raised to the power negative st, and this is multiplied by the sine hyperbolic of at dt. Alright, cool. So far so good. So what we have to do here, we have to recall the definition of the sine of at. So the sine hyperbolic of at, sine hyperbolic of at, this is the same as e raised to the power at minus e raised to the power negative at. This one is divided by 2. So this is the sine hyperbolic function of at. So the general one is that the sine hyperbolic function of x, this is equal to e to the x minus e to the negative x divided by 2. So this one is the sine hyperbolic function of at. So we are going to replace that in our integral and then integrate that. So let me call this one the Laplace transform of the function sine hyperbolic function of at. Let me call that one capital F of s as we have in our table. So this is the capital F of s, and this is equal to the integral from 0 to infinity e raised to the power negative st. And now I'm going to replace the sine hyperbolic of at with e raised to the power at minus e raised to the power negative at. This one is divided by 2 and then dt. Okay, cool. So f of s is equal to 1/2 is a constant. It comes in front here. We have the integral from 0 to infinity, and now we are going to have e raised to the power negative st. This is multiplied by e raised to the power at minus e raised to the power negative at. Okay, so now let's distribute this. F of s is equals to 1/2 the integral from 0 to infinity, and now combining this one is going to be e raised to the power negative st multiplied by e raised to the power at minus e raised to the power negative st multiplied by e raised to the power negative at dt. Cool. So f of s is equal to 1/2 all this one is multiplied by dt. I beg your pardon. Okay, cool. So now combining them using the laws of indices and splitting this one into two different integrals, we have this, the integral from 0 to infinity of e raised to the power negative into s minus a all times t dt. So combining this one using the laws of indices, this is what you get. Alright, and now minus 1/2 the integral from 0 to infinity of e raised to the power negative outside, we have s plus a, and this is multiplied by t and then dt. Cool. So s minus a, s plus a, all these are constants in the t domain, so we can easily integrate this. These integrals are now trivial. So integrating this one is going to be -1 all over s minus a, and then e raised to the power negative s minus a times t. We are done with the integration. Put the limits of integration from 0 to infinity. And now minus 1/2, integrating this one is going to be the same thing. This is multiplied by -1 all over s plus a. And then we have e raised to the power negative s plus a times t. The limits of integration from 0 to infinity. So far so good. So we have f of s, and this is equal to -1 all over 2 times s minus a. Okay, so here we are going to impose the assumption. So let's take the limit first. So we are going to take the limit as t goes to infinity, which is the upper limit of e raised to the power negative s minus a times t, minus the lower limit. When you plug in 0, this one here goes to 0, and then e raised to the power 0 is 1. So the lower limit is actually evaluating to 1. And now we have negative here, that becomes positive 1 all over 2 times s plus a. And now let's take the limit. So we are taking the limit as t goes to infinity of e raised to the power negative s plus a times t, minus plugging in 0 again. This one goes to 0 as t goes to 0, and then e raised to the power 0 is 1. Cool stuff. So f of s is equal to, so here we are now going to impose the assumption. The assumption that we are imposing here is that we are imposing the assumption here that s is greater than a, strictly greater than a, in order for us to solve this. So imposing that assumption means we now have this exponent is now going to be approaching negative infinity as t is approaching infinity. And as the exponent is approaching negative infinity, everything here is going to be approaching 0. Okay, cool. So this is what we have, and then this is greater than a, and then we are going to have negative 1 all over 2 times s minus a, right? And now this one goes to 0 as t goes to infinity, minus 1, and now plus 1 all over 2 times s plus a. And now as t goes to infinity, this one goes to 0 as well, because the exponent is negative infinity, so that is going to be 0 minus 1 as well. This is dependent on this assumption. So the assumption here is that s is strictly greater than a. Okay, cool. So now we have this. F of s is equal to, what do we have here? So this one is going to be positive number, right? So this one is going to be positive 1 all over 2 times s minus a. That is negative here. That becomes positive, and now we have negative 1 all over 2 times s plus a, like this. Okay, cool. So 1/2 is a constant and is common between the two terms. I'm going to factorize it out, and I'm going to have 1 all over s minus a minus 1 all over s plus a. This is now algebra. So the LCM here, we are going to take the LCM of s minus a, which is multiplied by s plus a. And when we divide, we are going to have s plus a on top here minus, this one is going to be, when we divide here, we are going to have s minus a, like this. And this is multiplied by 1/2 in front. And this is equal to 1/2. And we are going to have, the numerator is now s plus a minus s plus a, like this, all over the denominator difference of two squares. When we multiply them, we are going to have s squared minus a squared, like that. And this one is capital F of s, the Laplace transform of the function sine hyperbolic of t, at. So f of s is equal to, so 1/2, and then we are going to have 2a is left on top, and then we have s squared minus a squared. And this reduces to a all over s squared minus a squared. So this one is actually dependent on the fact that s is strictly greater than a. So this is what we have for the Laplace transform of the sine hyperbolic of at. Okay, s greater than a. So let's go to our table and then fill that. So here the Laplace transform of the sine hyperbolic of at is a all over s squared minus a squared. Okay, cool. So this one looks like the sine hyperbolic of the Laplace transform of the sine of at. So the next one is the cosine of at. Why not? So now let's switch colors. Let me do it in white pen. Why not? So we are now going to find the Laplace transform of the cosine hyperbolic of at, like this. And this one is equal to the integral from 0 to infinity of e raised to the power negative st. And now I'll have to multiply by the function, which is the cosine hyperbolic of at, and then dt. Now let's recall again. So we are recalling. So not actually recalling, but refreshing your memory with the cosine hyperbolic of at. This is the same as e to the at plus e to the negative at. This is divided by 2. So now let's replace that in our integral and now solve that. So the Laplace transform of the cosine hyperbolic of at, permit me to just replace that with the capital F of s, and that is equal to the integral from 0 to infinity of e raised to the power st multiplied by e raised to the power at plus e raised to the power negative at over 2 dt. Cool. So 1/2 is a constant that is going to come out of the integral. So we are going to have 1/2 here, then the integral from 0 to infinity. And now we have e raised to the power negative st times e raised to the power at plus e raised to the power negative st times e raised to the power negative at, all this one dt. Let's split this one into two different integrals. So we have 1/2 the integral from 0 to infinity, and now using the laws of indices here again, we are going to have e raised to the power negative outside. We have s minus a, all this one multiplied by t, and then dt. The next one is going to be positive 1/2, the integral from 0 to infinity of e raised to the power, laws of indices here, that is going to be negative outside s plus a, and then this is multiplied by t, and then dt. Cool. Now the same thing. So we are going to have 1/2. Now integrating is going to be negative 1 all over s minus a. So we just differentiate this one with respect to t, and then we divide, and then we repeat this because this is indestructible. The limits of integration from 0 to infinity, this is plus 1/2, and then this is negative 1 all over s plus a. This is multiplying, and then we are going to repeat the function e raised to the power negative s plus a times t, the limits of integration from 0 to infinity. Cool stuff. So f of s is equal to negative 1 all over 2 times s minus a. Cool. And now let's take the limit. So we are taking the limit as t goes to infinity, the upper limit of e raised to the power negative s minus a times t. Cool. Now minus the lower limit. The lower limit, when you plug in there, e raised to the power 0 is 1. And now this one is going to be negative as well. So this one is going to be negative 1 all over 2 times s plus a, like this. And now we are going to take the limit. So the limit as t goes to infinity of e raised to the power negative s plus a times t minus the lower limit, plug in 0, that is going to be e raised to the power 0, which is 1. Okay, so the calculus is done here. Next is now algebra. So negative 1 all over 2 times s minus a. Cool. Now as t is approaching infinity, this one is going to be approaching negative infinity, this one, and now everything here is going to be approaching 0. The assumption that we are using again for this is that the assumption that I'm using for this is that s is strictly greater than a. So the assumption here is that s is strictly greater than a. So when we have that assumption, this one is going to negative infinity as t goes to infinity. All right, cool. So now if we have that, and then this one is going to be approaching 0, and that is going to be 0 minus 1. And now we have minus 1 all over 2 times s plus a at the bottom here. And now this one goes to 0 as well as t goes to infinity. And now you're going to have 0 minus 1. So capital F of s is equal to, this one is now positive because negative, that becomes positive 1 all over 2 times s minus a. And now this one becomes positive 2. So this one is going to be equal to what really? So this one is going to be negative, negative, that becomes positive. Okay, cool. So that becomes positive 1 all over 2 times s plus a. Cool. So f of s is equal to 1/2 is common. I'm going to factorize it out, and I'm going to take the LCM, which is s minus a multiplied by s plus a, and then we divide. So dividing that, this one is going to be s plus a on top here, and now plus this one is going to be s minus a. So this is going to be equal to 1/2, and then the numerator is going to sum to 2s. And the denominator, those are difference of two squares. When we multiply them, that is s squared minus a squared. Cool stuff. So f of s, the Laplace transform of the cosine hyperbolic of t, this is going to cancel this one, and now what is left is s divided by s squared minus a squared, and this one is the Laplace transform of the cosine hyperbolic of at. Okay, cool. So now let me switch, and then we fill our table, and then we'll work few examples, and then wrap up the video. So this one, the Laplace transform here is going to be equal to s divided by s squared minus a squared. All this one is based on the assumption that s is greater than a. This one is based on the assumption that s is greater than a strictly. So this is what we have. So let's say you are given an example. So let's say we are asked to find the Laplace transform of the following hyperbolic functions. So let's find the Laplace transform of the sine hyperbolic function of, let's say, 2t. Why not? So this one is going to be equal to what really? So that is going to be, so here a here is equal to 2. Our a here is equal to 2. We just replace it here, and now we'll be able to solve that. So a is 2, so that is going to be 2 divided by s squared minus 2 squared. So that is equal to 2 all over s squared minus 2 squared is 4. And this one is the same as capital F of s. So the Laplace transform of the sine hyperbolic function of 2t is 2 all over s squared minus 4. Now, what about the Laplace transform? So the Laplace transform of the cosine hyperbolic of, let's say, 70. Why not? So how do you find a cosine hyperbolic of 70, the Laplace transform of that function? So we are going to use this. A here is equal to 7. So we just replace it there, and now we are going to have s divided by s squared minus a squared. A is 7, so this is equal to s all over s squared minus 7 squared is 49. And this one is equal to capital F of s as the Laplace transform of the cosine hyperbolic of 70. Yeah, so this is how to solve the Laplace transforms of hyperbolic functions. So we just start off with the definition, and then we plug in the functions, and then we'll be able to integrate that based on the condition that s is strictly greater than a. Yeah, so in my next video, I am going to now solve the Laplace transform of exponential function multiplied by trig function and hyperbolic functions. So if you enjoyed this video, you consider subscribing to Calculus Diaries, and then I will see you in my next video. Bye bye.